So I guess with the 5 minutes delay, we can start with our second seminar of this year in Continuous Data series. And today we're glad to have Ginevra Carbone here with us. And just a very brief introduction about her. She studied mathematics at the University of Udine and then moved to Trieste, where she earned a master in data science and scientific computing. And currently she's pursuing her PhD studies, generally speaking, in the field of deep learning under the supervision of Luca Bortolussi. And today she will talk about general adversarial attacks, which is a hot topic, especially in the for its implication for security reasons. And now I just leave the floor to Ginevra and welcome her.
Thanks for the detailed introduction. So today I would like to present a few programs that I've been working on lately, and let's say they all revolve around the same topic, which is the robustness and the interpretability of neural networks under adversarial attacks. So first of all, I would like to start with a very basic introduction to image classification by means of neural networks and how loss optimization works. So sorry if this introduction is trivial to some of you, but I want to make sure that, let's say, we are on the same page. So let's suppose that we want to perform image classification on a data set of images. So, for example, we have this input image X, which is a bird, and we want to be able to associate a probability vector to this input image X. And why is called a probability vector? Because all the components in this vector sum up to 1. So they represent the probabilities that this input image X belongs to each one of the classes. So, for example, in this case, we have a 95% probability of X being a bird and 5% being a horse. And how can we formalize this kind of reasoning? So we want to define a classifier, F, which takes as input X and gives as an output Y. Now, X is an image, so we want to give a vector representation to this image. And what we do is we associate a real number to each one of the pixels composing this image. I hope you can see my pointer. And so basically, if we read the lines of this matrix by rows, what we obtain is, in general, a two-dimensional vector with real components. So that's why F belongs to R to the power of P. Then the probability vector is an element in R to the power of K, where K is the total number of classes. So in the end, what we do during training is learning the best fit of a certain function F to a set of observed data. So this observed data is a set D of couples xi, where x is always an image and y is always a probability vector in general, which is one octet code. So it means that this particular probability vector has all 0 components except for the correct class, which is 1. And now the function f is parametric because f in general is able to compute the output y by means of complex computations, which also involve this matrix of weights called W. So learning the best fit means learning the best parameters W that are able to define this complex relationship. So in particular, we want have to have a certain, let's say, architecture, which is the one provided by neural networks. Now, let me just briefly describe neural networks in really 2 sentences. And we can say in general that neural network is a composition of functions. So the F1 and J in this case. And they can be, the nice thing about neural networks is that they can be graphically represented, as you are seeing here, as a collection of nodes called neurons. And the reason why they are called neurons is that this particular structure is inspired by, let's say, neural networks in the brain.
So suppose that in particular we want to compute the value of one of the neurons in this network, which is called Zi. Now you can see that Zi is connected to all the neurons in the previous layer, which are called here uj. And these edges are all weighted. So it means that we can write Zi as a linear combination of uj by means of W parameters plus nonlinear activation. So in this case, the nonlinear activation is this function sigma, which is a sigmoid function. But of course, in general, you could have many different types of nonlinear functions. And the reason why we are using this kind of linear combination is that, or better, nonlinear combination, it is that we want to let's say, to define a very complex relationship between X and Y. And in the end, what we obtain is a vector with the same number of components as the number of classes that we pass through a softmax function. And this particular function is able to convert the output into a probability vector. So to make sure that all the components sum up to 1. Okay, so the question now is, supposing that we have this fixed data set of couples X and Y, how do we learn, in fact, this matrix of parameters W? So we perform loss optimization. Now, learning in general, learning through a training algorithm means taking into account the training data and learning the best fit of F. So we are doing this by means of loss functions. There are many possible loss functions, and each one is more suitable for a certain application. And in general, they all measure the difference between the predictions provided by our model F and the true outcomes which are provided in the training dataset. So our goal during learning is to minimize this loss function, so this discrepancy between the two outputs. And we are searching for the best parameters W in the parameter space that satisfy this property. Now, of course, you cannot explore all the possible values of W. And this is why, in practice, we usually use stochastic optimizers, like stochastic gradient descent or other more advanced techniques. And this means that we start from a random initialization of the weights in the weight space, and then at each step of this iterative algorithm, we optimize the function L by moving in the direction of the gradient. So we take small steps in these directions and update each time the values of those weights. Now, you can see that there is an additional parameter called gamma, which is known as the learning rate, and it is responsible for the speed of learning. So if we use higher values of gamma, then the update of these values of W is quicker. Okay, so that was a very basic introduction to image classification. And now I would like to talk about adversarial attacks, which are the main concepts that we are dealing with today. And I also want to describe a few geometric properties related to the data manifold. So an adversarial attack in general is a small perturbation of a test input, which in this case is an image, that leads our learned model F to a misclassification. So, for example, suppose that you have this original image, which is correctly classified by the model F, which we already learned. And then we add this small noise, which is an adversarial noise, and obtain a new image, which is visually very similar to the original one, but is misclassified by the model and also with very high confidence. So, of course, there are many consequences to this problem, because many AI systems are perceived as unreliable, especially if you are dealing with security-related settings, like, I don't know, self-driving cars or medical imaging and so on. So we want to develop some techniques that are able to guarantee robustness under certain conditions. Now, a very basic example of adversarial attack is a fast gradient sign method. And it is the first attack ever formulated. And it is also computationally very efficient because it only involves one gradient computation per each input sample. And in this case, we start with the fixed weights W of our network and then perturb X in the direction of the greatest loss. So basically, this is similar to what we were doing during loss optimization, but instead we are computing the gradients with respect to the input X instead of the weights. So of course, there are many other possible adversarial attacks that we could define, and they all have different degrees of knowledge about F, about the learned function. And in this case, we talk about a white box attack because it has access to all the possible informations about F, like the weights, the values of predictions, and so on. But in general, there are also very strong attacks which do not require this high level of knowledge. Okay, so do you have any questions? Is it all clear? Also from home, if you have questions, just stop me at any time. Okay. So from a geometrical point of view, we know that we can rely on the manifold hypothesis. So it states that our data is always sampled from a low-dimensional manifold, which is embedded in a high-dimensional space. Now, let me explain what this means. And so first of all, a manifold is a particular geometrical space which has many nice properties because it is locally Euclidean. So it means that we are able to define distances, angles, many other things. And we suppose that, of course, the input space is high dimensional because, as we already said, we associate a very big vector to each one of the images. And then we suppose that the data is actually sampled from a space which is low dimensional in RD. And this is because, let's say, we suppose that the minimum number of dimensions which is required to represent this data without losing any information is much lower than the original dimension. So this is the main assumption we are doing. And another thing that we know is that adversarial perturbations usually are found in the directions which are normal to the data manifold. And this has been observed experimentally in multiple works. So a first, let's say, consideration that we do is that as the codimension between this low dimensional space and the embedding one increases, there is a high chance of selecting adverse directions even randomly. So if we randomly take directions in this space, with high probability they are, let's say, they are significant from an adversarial point of view. So this is the main property that we are leveraging in our techniques. Okay, now I want to present a few methods to achieve adversarial robustness. And the first one is adversarial training, which is a state-of-the-art technique, very well known. And then I'm proposing an ensembling and randomization technique. And finally, talking about the properties of Bayesian neural networks. So adversarial training is a very simple technique because let's say it allows to convert any attack into a defense, because each time that we generate a certain set of adversarial attacks, we add them to the training data and use it to train a new model. So for example, here we have a test set, which is the first column here, and a few attacks like FGSM, PGD, which is projected gradient descent, deep full attack, Carolinian-Wagner attack. And let's say we add these adversarial attacks to the training data. So it's like we are performing a sort of dilation of the data manifold, because we are adding a few new samples which presumably do not belong to the original low dimensional space. So this is, of course, a very good idea, and in fact, it's considered to be state-of-the-art. But the problem here is that it tends to overfit the chosen attack, meaning that if we add samples generated using a particular attack, and then we attack the resulting model with another method, then probably it isn't so, let's say, resilient as it was on the original attack. So we want to overcome this problem and define a few techniques that work in general, so that are not adversarial dependent. Now, the first idea is to use random projections of the training points as adversarial features which are attack independent. So let me explain what this means. And first of all, we can represent our training data in matrix form. So suppose that we have a matrix which where D is the dimension of the original images and N is the number of training points. And then we can define a Gaussian random matrix in R to the power of D times K. So D is the original dimension of the space, and K is a lower number. And basically, what we want to do is to project the training data X into a space of dimension K, which is smaller than D. And how do we build this random matrix? We simply sample all the entries of this matrix from this particular Gaussian distribution. And we know that when D is very high dimensional, there are many nice properties about this kind of random matrix, because first of all, we know that randomly chosen vectors in a high dimensional space are almost orthogonal. So with a very high probability, close to 1, they are orthogonal to each other. And this allows us to define projections without any orthogonalization procedure of the high dimensional matrix, which is a big advantage from a computational point of view. Then we know that this kind of random projection is able to preserve pairwise distances between points, meaning that if we observe a certain distance between 2 points in the original space, then it is almost preserved in the lower dimensional space. So finally, as we already said before, we know that as the codimension increases, there is a high chance of randomly selecting adverse directions. So if we use this matrix to project our data X, then we know that with high probability, we are moving in directions which are adversarially significant. And this is why we expect to get a few benefits in terms of robustness from this kind of reasoning. So we proposed two techniques which are both based on random projections of the training points. And the first one is an ensemble technique. It's called random projection ensemble. So it is a fine-tuning technique that improves the robustness of a pre-trained network. And basically, it projects the training data into multiple random subspaces, all different from each other, because the matrices are always sampled randomly. Then we train a classifier in each one of the subspaces, and notice that this procedure is completely parallelizable because all the subspaces are independent from each other. And finally, we perform an ensemble classification on the test input, meaning that we compute a prediction from each one of these, let's say, projected classifiers in the subspaces, and then sum up the probability vectors that we obtain from each one of them to achieve our final classification. And the second technique that we propose is a random projection regularizer. So this instead is a regularization technique, meaning that during training, when we are optimizing the loss function, we also add a regularization term, which is defined using these projections of the inputs. So in this case, we are trying to minimize at each step of the update the variation of the loss across all the projections in the subspaces. And in both cases, we were able to achieve some good results in terms of robustness. And this is just a plot for the RP regularizer method. So let me just show this one. And so basically what I'm showing here is the test accuracy achieved by two regularizers that we trained using uniformly sampled number of projection and size of each projection at each training step. So at each time, at each mini batch update, we are randomly sampling these two hyperparameters and then updating the weights. So we are computing test accuracy on the test set, on FGSM attacks to the test set, PGD attacks, and so on. Now, the two red lines are the regularizers, because we actually proposed two regularization techniques, one of which is the one I showed before, and we proved that they are equivalent in the limit of infinite k. And so I just showed the first one. And so we are comparing the regularizers to a baseline network, which is simply obtained with deterministic training on the training set. And then I'm comparing it to adversarially trained networks. So for example, FGSM robust is trained on FGSM attacks, the full on the full attacks, and so on. So what we expect is that FGSM robust network, for example, should be the best performing one against FGSM attacks. And this is the case, in fact, as you can see here. But in general, this property does not transfer to all the possible attacks. So if we attack this network with PGD, you see that the accuracy drops. Instead, our method of regularization is achieving pretty good performances in multiple settings without knowing anything about the attacks. So only using randomization. Okay, so that's the first thing that I wanted to show. Now let's move to another topic, which is Bayesian neural networks. Do you have any questions? I'm always asking. Yes.
What is the evolution of this sensitivity to adversarial attacks during training?
So you are asking if we checked this evolution of the test accuracy basically during training. We did not do this. We did not check during training how it was improving.
The issue is that, for example, if you are at half training, for example, the situation could be less severe than you are really trying to a very low value of the loss function. But this is just a geometric intuition. I don't know if that's true.
You mean because maybe we observed, let's say, a lower number of random subspaces, so there is, we are bad at generalizing after only a few iterations? Or you mean?
No, maybe. Let's see, maybe I'm expecting that the gap between the test set accuracy on unperturbed data and on perturbed data is less severe in intermediate states of training than at the end, where the model is very.
It could be. It's a reasonable assumption, I think. I don't know how to answer. I should check. Thank you.
Maybe it's not a really interesting question, but when you are attacking the adversarial defended or RP regularized network, you're using attacks generated against that same network or against the original?
The original one. Always against the original one, yes.
Are you eventually aware of results where attacks are actually generated on the RP regularized network?
I'm sorry, I'm accepting some new people. Oh, okay. Sorry, let me check. I have a message. Okay. I understand your question. Now, actually, the attacks are performed against the two regularizers in the case of the regularizers, but not in the case of robust models. So yeah, sorry, that's the difference. So the answer to the first question is no. It's against the regularizers that we perform the attacks. Yeah. there was another question.
Something more philosophical, my bad.
Yeah.
So the first.
No, you're good. It's okay to do other questions.
No, at the very beginning, you started showing the example of the
yes.
whatever that is changed, and to my side, nothing changed. So, and nice, and the learning you're doing is supervised learning, which means that there is someone from external giving output. This is a 9, this is a 1, whatever. Now, when you show some examples of attacks, the example that is actually say that is not a 9 anymore. So if the attack puts actually the example, what is the meaning of the past? You expect an attack that.
Because in general, you see this drop in accuracy even when like the difference between the perturbation and the original image is almost undistinguishable. So the problem is that when you have very small perturbations, like this is an extreme case in which I just wanted to show graphically the difference between a few attacks, but in general, the problem is that you cannot even recognize them just by looking at them.
So the attacks you're using are not going to be strong.
Exactly. Okay. So I guess I can go on. Now, yes, I wanted to talk about Bayesian neural networks, which is one of the main topics that we worked on. And there is a substantial difference between how deterministic neural networks and Bayesian neural networks are trained. Because in a deterministic case, we are trying to learn a set of fixed parameters for our network. So we have this parametric function f, and we want to learn a fixed set of weights w. Well, in the Bayesian case, we suppose that the weight matrix is a random variable. So it means that we have a probability distribution placed on each one of the weights. And what we are learning, in fact, is an ensemble of parameters. So how are we learning this kind of function? First of all, we start from a prior distribution, which is placed on each one of the parameters. And then we use Bayes' theorem to update our belief about the value of these parameters and by computing the likelihood function. So we compute the likelihood of W with respect to the observed data. And finally, thanks to Bayes' theorem, we obtain a posterior probability distribution. So the problem here in this formulation is that in general, computing this normalization factor PD is an intractable problem because we would need to integrate over all the possible values of W. So this problem, of course, is intractable in deep neural networks where we have a very high number of weights. And what we are doing instead is to rely on some approximate inference techniques. So let me just briefly, very briefly and generally describe a couple of approximate inference methods because we use them in our experiments. So our goal here is to find an approximation to the true posterior distribution. And let's say that we have two possible ways of doing that in this case. So the first one is Monte Carlo sampling. So it is a Markov chain Monte Carlo technique where we are just computing a few values sampled from this distribution. So we do not actually know the shape of this distribution. We are only sampling a few values. And the nice thing about this technique is that in the limit of infinite samples, so if we take an infinite number of points, then this procedure converges to the true posterior distribution. And also it assumes, as we said, no model for the posterior, so it only takes single samples. And it's very good at capture multimodal distributions. The problem with Monte Carlo techniques is that they are on the more expensive side. Then we have variational inference, where we basically transform the problem of Bayesian inference into an optimization problem. So in this case, we compute an approximate posterior, which has a predefined shape, because it has to belong to the set of variational distributions. So before, let's say, learning our approximate posterior, we decide the shape that we want it to be. And for example, usually it's a Gaussian distribution. And this technique is very efficient, but of course, if we choose a family of Gaussian distributions, the posterior is unimodal. So in our experiments, we are using both of them because they have different kind of, let's say, drawbacks. And of course, variational inference is more efficient, but also less reliable in general. So the question is, if we have Bayesian neural networks, how do we compute a prediction on a new observed point? Because we do not have a certain fixed function f. We have probability distributions over all the weights. So what we do is we use a posterior predictive distribution, meaning that each time that we want to compute the probability vector of a new sample, we take multiple, let's say, deterministic networks from these probability distributions, because each time we are sampling all the weights again, and we repeat this n times, and finally obtain n copies drawn from this distribution, and perform an ensemble classification from all these networks. So we average out the predictions, and we obtain our final Bayesian prediction. Now, of course, if we want to perform adversarial attacks on a Bayesian neural network, we don't want to attack the deterministic function anymore, but we want to attack the predictive distribution. So we compute, instead of computing the gradient of the loss, we compute the expected gradient of the loss over multiple samples from the posterior. So that's the only difference. And in this way, we are able to transfer any kind of deterministic attack into the Bayesian setting. So our main theoretical result is that we proved that in the limit of infinite samples from the posterior, the Bayesian neural networks are resilient to adversarial attacks, which are gradient-based. So only to this specific class of attacks. And in fact, if you suppose that MD, which is the space from which the data belongs, is a smooth data manifold, and the prior distribution PW is uninformative, then we also assume that F is overparametrized. And so I will explain all the meaning of these terms in a bit. Then we know that in this overparametrized and big data limit in general, we know that the expected gradient of the loss is 0. So any adversarial attack which is gradient-based, so which involves this gradient computation, is ineffective. Now, this is a let's say an extreme theoretical setting, but we actually observed that this property holds in general, even with approximate inference techniques. So basically, let me just give a few informations. An uninformative prior is simply a distribution which is flat over the real line. Like, for example, it could be a wide Gaussian or uniform distribution. And F overparametrized means that the number of weights is always bigger than the number of observed data points. And then at full convergence of the training, F is at full convergence of the training algorithm, means that it always achieves 0 loss on the data manifold. So each time that we are sampling a set of weights from the posterior distribution, then the function that we obtain is at 0 loss on MD. Okay, so let me show a few results which confirm this kind of behavior. In this first plot, we are testing the overparametrized limit. So we trained here a set of 36 BNNs with HMC, with an increasing number of training inputs, which are represented by the color, and a different number of hidden neurons, which is a hyperparameter that we added to our architectures. And all the BNNs represented here also have different architectures. So each one of the dots is a different network, Bayesian neural network. Now, we are computing the gradients of the loss with respect to the input. Sorry for the different notation. This just means the expectation, an expected value, on a half-moons dataset, which is a dataset of bidimensional data points. So we are visualizing both of them. And as you can see, if we go towards the overparametrized limit, all the components shrink to 0, which is what we proved theoretically. Now let's look at the single components of this gradient of the loss. So each one of the components in the vector, if we compute the components of the expected gradient for an increasing number of posterior samples, which you see on the x-axis, then all the components go towards 0. And this holds in multiple settings. So here you can see this for the case of MNIST and fashion MNIST datasets. So for each point, we have 1,000 test points, and for each one of them, we have a very big number of components. So we are, let's say, we are visualizing all of them. And finally, the last thing that we observed about Bayesian neural networks is that there is a particular, let's say, behavior that holds for Bayesian neural networks, but not for the deterministic ones. So in this case, we are, let's say, we are studying the correlation between test accuracy and robustness. Robustness here is defined as 1 minus the softmax difference, which is the difference between softmax predictions on the original points and softmax predictions on the adversarial points. So we are simply computing the difference between the probability vectors given on the original data points and the probability vectors given on the attacks. So 1 minus this difference is the robustness we achieve. And in the subplots here, you can see the blue dots, which are deterministic neural networks, and the red dots are Bayesian neural networks trained with HMC in the first column and with BI in the second one. So you can see that in a deterministic case, which is the blue one, there is a trade-off between robustness and accuracy. While this trend does not hold for Bayesian neural networks, and it's completely reversed in the case of HMC, which gives more accurate posterior approximations. So this is a first interesting observation, because it means that if we want to obtain a robust neural network against a gradient-based attack, then the best choice, at least for the case of HMC, is to search for very accurate models. And with high probability, they will be also more robust. Okay, so do you have any question? Someone from home? Okay. Now, the last part of this presentation is about interpretability of neural network and the stability of Bayesian interpretations. So the idea is that ideally we would like to have classifiers which are interpretable. So each time that they perform a certain decision, we would like to know why this decision was taken. And in particular, we rely on layer-wise relevance propagation, which associates a relevance score to each pixel in the image X. So you can see that the relevance is positive when it contributes positively to the classification, and it has a red color in this case. It is negative when it contributes negatively, and 0 when it has no impact. So no impact is the white color, and negative is the blue color. So we are also able to visualize this kind of computation through the heat maps associated to the original images. Now, in general, LRP has to be conservative, meaning that we want the let's say the relevance scores assigned to the pixels to be consistent with the predictions. So they have to satisfy this conservative property. And there are many possible rules that we can use in practice to compute LRP according to this property. But for simplicity, let me just describe the epsilon rule. So it is an iterative method that starts from the output predictions. So in the graphical representation of a neural network is the last layer, the one before computing the let's say the softmax prediction. And at each step, it backpropagates the relevance scores in all of the previous layers. So each time we are starting from the softmax, computing the relevance score for all the feature representations in that layer and going backwards toward the input. Now, the question is, we know that LRP interpretations are unstable under perturbations of the inputs, and this has been observed in multiple works. Which means that if we take a certain image X and build an adversarial perturbation, then the associated relevance scores are very different from each other, even if the two images are almost identical. So the question is, are we able to, let's say, to find a connection between adversarial robustness and the stability of interpretations in this sense? So the stability, the similarity, let's say, between these two relevance heat maps. The answer is yes. And in particular, we study the stability of Bayesian interpretations based on our previous theoretical finding. And in order to, let's say, to measure this improvement in the stability of interpretations, we define the LRP robustness in the following way. So we consider the two heat maps R and R tilde X associated to the original image and to the adversarial one, respectively. And then we compute. You have a graphical representation of this on the right. We compute all the relevance scores associated to both of them and see how much they agree on the relevance of pixels. So we find the set of k% most relevant pixels in both images. And we do this in by computing the absolute value of the heat maps, because we want to take into account both most relevant pixels in both the negative and positive sense. So we believe that also negative contributions to the relevance are important. And so this is just, let's say, the percentage of most common relevant pixels in the two images. And this is our measure of robustness. Now, it's easy to transfer this definition to the Bayesian setting, because as we did for adversarial attacks, we simply compute, in this case, the expected heat map. So we sample multiple values of the weights, and for each one of them compute a different relevance heat map, and then average out the relevance scores. And so, of course, also LRP robustness can be computed in the Bayesian setting. Another thing that we want to analyze here is the stability of feature representations of the internal layers, because yes, we are able to associate some relevance heat maps that backpropagate starting from the softmax value, so from the prediction, but we also want to analyze how the internal representations are affected by let's say, these adversarial attacks. So we associate a heat map representation to each one of the feature vectors. And let's say that we also observe stability in this sense. In fact, in general, we proved that theoretically, in the same limit that we were talking about in the previous theorem, so in the infinite data overparametrized limit, we proved that explanations usually move in the directions that are tangent to the data manifold in that point, because all the orthogonal components average out to 0. So the expected LRP heat map is always parallel to the data manifold. And this is what we observed in practice. So in this plot, we are comparing the LRP robustness of Bayesian neural networks to that of deterministic neural networks and adversarially trained neural networks. And in particular, we are computing for each point the point-wise difference between these robustness scores between adversarially trained and deterministic network in the case of the orange distribution, and between Bayesian neural networks and deterministic neural network in the blue and green, let's say, case. So you can see that in general, in the under the Bayesian framework, this robustness difference is higher. So it means that they are more robust. And this holds in each one of the representations in the internal layers. So let me just show you another plot, which is basically saying the same thing, but for different rules that are used to compute the LRP. So here we have the epsilon rule, gamma rule, alpha beta rule, and so on. And so the first column is the difference between adversarial and deterministic LRP robustness, and the second one, Bayesian and deterministic ones. So here we are analyzing a different data set in each row. The first one is MNIST, then we have fashion MNIST and Cipher 10. And for simplicity here, I'm always showing the last representation. So the traditional definition of LRP robustness in the last layer. So in general, we notice that Bayesian explanations are more stable also in practice. And so here we are instead looking at the correlation between LRP robustness and softmax robustness. So the softmax robustness is the same that we talked about before. So it's the 1 minus the softmax difference, which indicates the stability of predictions of our neural network, while LRP robustness is the stability of explanations. So what we see in general is that there is a correlation between these two quantities in the Bayesian setting, and especially as the number of samples increases, while it doesn't hold for deterministic and adversarially trained neural networks. So the Bayesian ones are, as in the previous plots, the blue and green, and orange is adversarially trained, pink is deterministic. So this is another interesting finding. So this concludes the presentation. Let me just do a recap of what we saw. So we started from random projections of the training data and showed how they are not only a dimensionality reduction technique with all the computational benefits, but also are able to catch some attack-independent adversarial features. Then we saw how BNNs in this theoretical limit are robust to gradient-based attacks. And even though we did some strong assumptions from the theoretical point of view, then in practice we observed that this, let's say, this adversarial robustness holds even when we are using cheap approximate inference techniques like Bayesian inference. And then we noticed how high accuracy is a good indicator of robustness for BNNs. And finally, we saw how Bayesian interpretations are more stable in general, and how also interpretations are in general less robust than classifications. So that's all. These are the references of the works basically that are described in this presentation, and I'm waiting for your questions. Thank you.
Thank you.
I'm opening the chat also if you want to write there.
Good afternoon. Can you hear me?
Yes, I do.
Thank you so much for the presentation. I would like to ask just to cope my ignorance in the matter, the subject. Which are the most practical use you can on which you can apply this kind of analysis?
It depends on which kind of analysis between the ones we talked about. Because, for example, the observation we did about Bayesian neural networks in general is a very strong one. But the problem is that in the Bayesian setting, there are many problems for a computational point of view. So if you want to use them in practice, they are not really applicable right now. But yeah, because we only worked on very small and simple data sets. We did not go beyond cipher 10, so we were not able, for example, to achieve very high accuracy for data sets like ImageNet. So we are far from the practical applications in the Bayesian framework. But the first one about random projections is maybe less, is not supported by theoretical proof, but it's way more efficient. So it could be used in practice in any security-related setting.
Okay. Understood. Thank you so much.
Thank you for asking. Okay, I think there are no questions.
Maybe a more speculative question. I'm not really familiar with the proof of robustness of Bayesian neural networks to Bayesian-based attacks.
Okay.
But considering more recent trends about, for example, lottery ticket hypothesis, or even better, the lottery subnetwork hypothesis, do you can envision some sort of dependence of the properties you observe on Bayesian neural networks only on a subset of weights being Bayesian, whereas a majority, for example, of other weights just being a maximum posteriori or maximum likelihood standard estimation of?
Yeah. Well, the answer is I started working on this exact problem, and I don't have an answer right now, but I think it should be working. Yes, maybe you are farther from the theoretical limit, because in general you want overparametrized neural net, so a very big number of neurons which are Bayesian, but I think that it should hold at least for those weights. So it means that if we notice that these components average out in expectation, then it has to hold at least on the Bayesian weights. So it means that only the deterministic ones, the ones that are fixed, are left out from this property. So if you use a very high number of Bayesian weights, maybe not every one of them, it should work. You should see an improvement in robustness. Okay. I think there are no more questions, no? Okay.
Just to know, maybe, so when you talk about the random projection, no?
Yes.
There you train an ensemble of
yes.
No? And how do you choose the number that you project?
I should have an additional plot because I did some extra slides. Yes, so for example, this is RP ensemble on a high number of combinations of number of projections and size of each projection. So the answer is we tried of multiple combinations. And this is what we saw. And in particular, we observed that if you keep the number of the dimension of the projected subspace very low, we also observed, which is the K parameter, we observed that from a computational point of view, the time it takes to train this kind of ensemble is identical to the baseline, to the deterministic network, but you achieve a very high improvement in robustness. So you simply try on multiple combinations and tune the correct parameters.
And does it have a relation with the intrinsic dimension of the manifold, or?
Yes, it should, because basically it means that also in this case, it's like you are trying to, let me explain about an intuition. Let's say you are leveraging the fact that the codimension is very high, and so when you are randomly selecting these directions in the space, you are leveraging the fact that they are in fact adversarial with high probability, and this is a consequence of the manifold hypothesis, because it is related to the intrinsic dimension. It is exactly about the intrinsic dimension of the data points. So yes, it's related.
Probability is that because I don't understand fully. Like it's quite surprising that you choose like a subset of random directions, and still because you defend against like a almost infinite.
The key fact is that it's a high dimensional space. If it wasn't high dimensional, then this would not hold. Yeah.
I'm wondering something.
Yeah.
If you have a neural network that's more robust against attacks and more could that also mean that it's more robust? For example, if I have different types of images that come from different detectors that maybe have different types of noise.
Okay, so that they are, sorry, they are different attacks which are performed on different architectures.
But for example, I take an image with a detector that has different characteristics.
Okay,
so
yes.
That will of noise to that image. So this type of network could also be robust against that type of noise.
Yes, it should be in general. I mean, there are a few transferability properties that hold. So in general, you see a small improvement in robustness even on different attacks. But from a theoretical point of view, it's always linked to the attack that you trained on. So it's not, let's say from a theoretical point of view, it's not elegant because you're not generalizing, you're only training on more samples, new attacks, new, yeah. I don't know if this answered the question, but okay.
Yeah, just it's slightly off topic, let's say, but just to expand a little bit the team. Does exist any model which is inspired directly from neuroscience observation that is also efficient in containing a little bit of adversarial attacks, because we are very reliable in this sense. Our vision system is very robust to, let's say, ordinary perturbations. And since these attacks will sometimes are also undetectable conceptually from us, we are. So I guess if there is any relevant model which is inspired to neuroscientific data.
Are you thinking about any specific application in neuroscience or in general? Visual applications. I'm not aware. I don't know, really. I don't know the answer to this question.
Maybe biological inspiration in this case didn't have that much, at least at this moment. Okay.
Well, if I may say something, there was that paper probably already talked with that proposed to replace activations of neurons with layer-wise K-top activated neurons.
Okay.
To zero all the others, but it's still required adversarial training.
Okay.
And you're saying somehow competitive results, and it was directly inspired by lateral inhibition of neurons, but it was more an engineering directly inspired by biological mechanisms that I'm aware of.
Thanks.